And, okay, and I'm going to try to share my screen. Whoops, it's disabled. So,
oh, my apologies.
You should be
Okay,
able to
try again now. Yeah.
is it ready? Okie doke. Alrighty, so I'm just going to start where I left off yesterday. And I'm going to give you all two options because I clearly have too much material to cover. And so we should see about where I am after an hour or 45 minutes, and then decide whether I should just run on or if we should convene again tomorrow. Okay? But we got yesterday to the point of talking about Hutchinson's and Lewis's schemes, and I gave you some examples of polymictic lakes and dimictic lakes and more monomictic lakes. But as we study ecosystems, we often really need to know how frequently does vertical mixing occur, during the stratified periods. And can we predict the depths over which water is exchanged? And can we predict the coefficient of eddy diffusivity, known as Kz? And is there horizontal exchange? Okay, so these schemes help us to a certain point, but we've got to go farther. So in the following, I'm going to talk about vertical exchanges, and starting off, thinking about the movie from Ben Hodges, that the thermocline rocks up and down in response to wind. We call those ensuing motions internal waves, and except when the mixed layer deepens from cooling, they mediate vertical exchanges. So again, for some of you, this is review, and for some of you, it's the first time you've ever seen it. So I've got to make sure that I cover all the bases. But the simple sketch, epilimnion, thermocline, hypolimnion, the wind blows, it tilts the thermocline, and then when the wind relaxes, it goes the other direction, and you can have more than one node and more complex internal waves. And this is some data from Lake Ontario, showing you then a time series with some internal waves, and you can see the very regular pattern of this up and down motion, of the thermocline in response. Well, if the wind stops and the motions keep going, we would call it a seiche. And if the wind every day was pulsing at about the same time, we might call that a forced internal wave, right? So we do have some differences in terminology that we use. And then when these waves become unstable, if there's too much shear, like a really strong velocity gradient in them, as sometimes can happen when you've got these other little waves on top, then they might become what we'd say unstable and mix and have some turbulence, and then you might get a flux through the thermocline. So what we want to do is begin to understand the conditions that will let that flux occur and how much. And here's where we get into using the dimensionless indices. And there's a lot of these. And they're just a very, very common tool in environmental fluid dynamics, engineering, applied math. And when you get all the units, they cancel. And the nice thing is, when they're well designed, they apply to a lot of different flow regimes. So the Wedderburn number, I'd love to know how many of you know it, but I can't see a whole set of hands up even. But anyhow, it's gravity over density times the density difference across the thermocline times the mixed layer depth squared divided by a friction velocity, which as a rule of thumb is about 1/1000th of the wind speed, and it's squared divided by the length of the lake. And if we look at this, we could say, oh, a strongly stratified lake might have a high Wedderburn number, okay? And that's that delta rho. But then if it was super windy, that can drive it down. Or if it's a really, really long lake, that will drive it down. So with all those different factors all interplaying together, that determines the amount of thermocline tilt. And in fact, the thermocline tilt, I think it was Ulrich asked me about that yesterday, is usually 1 over the Wedderburn number, more or less, okay? Now, after coming up with the Wedderburn number, right? Then we got the lake number, and it's an integral form, right? It's more complicated than that. The equation is kind of gnarly to talk about in a talk, so I never really even bothered to show the equation. And some of the lakes in which I work, if I calculate the Wedderburn number and the lake number at the same time, they're identical. And other times they differ. And there's a reason. And if we have luck, I'll get to that today. But this is a set of sketches that I developed based on my own experience, but also some of the fundamental ideas that were in the paper of Spiegel and Imberger in 1979, and Steve Monesmith's laboratory experiments in 1986. And then these papers are actually from some of my work at Mono Lake. So again, think about a lake. If that, I'll just say Wedderburn number here, if it's greater than 10, when the wind blows, you'll get some currents generated up here near the surface, but the thermocline may not tilt. Now here, this greater than 10, you might get a little tilting when it's 12, okay? But so this is sort of a rule of thumb. Then, once you're in a regime where the Wedderburn number is between around 2 and 10, when the wind blows, you begin to tilt that thermocline and you create a little bit more shear. And notice I put, describe any internal waves that form here as linear, and the molecular the coefficient of eddy diffusivity would be the same kind of rate as molecular movements, you know, the bouncing around of molecules. But as the Wedderburn number goes down, we get nonlinear internal waves, and the eddy diffusivity begins to increase. When it's about 1, you get a full upwelling. And now we're starting to get in a position where we can have water from the hypolimnion come up and maybe flow into and mix with the epilimnetic waters. And then the same thing on the other side, where some of this water from the epilimnion might go down and mix with some of the hypolimnetic waters. But here, I still have most of the shear. Well, the shear might even go all the way across the thermocline. Those waves will be nonlinear, and the eddy diffusivity is going to be a lot more. And then the last one, this one's been kind of interesting for me. The way it was presented, especially in Spiegel and Imberger, is when the Wedderburn number is much, much less than 1, the lake will fully mix. And if we get to the end of my talk, I'll show you some cases where we're pushing that. And sometimes the lake does fully mix, and sometimes it doesn't. Okay. I put this in again so we at least have some figures. You know, when hydrodynamicists want to sort of push the envelope and really understand some of these flows, they do experiments in laboratories. So this is an image of the experimental flume at the Center for Water Research at the University of Western Australia, where a lot of work was done to further interpret how these Wedderburn numbers. And so it's a big tank, and you can see it's connected with computers, and there'll be a layer of water on the bottom, which is dense, and a layer on the top, which is less dense. And you vary that, right? And you vary the angle of tilt. And from that, you can take photographs. And of course, then you also have conductivity and temperature probes and some wave gauges. And you begin to get an understanding of how the internal waves, you know, these ones that are riding along a density interface, how they actually change as a function of forcing. Then, in a minute, I'll show you a dimensionless figure related to this. One of the first people using this at CWR was David Horn. So then he went back and read a whole lot of theoretical papers. A lot of fancy equations like the Korteweg-de Vries equations, and he came up with scaling arguments, okay? And then Leon Boegman then did a whole lot of additional work, giving us more context. But the diagram that resulted from David Horn's thesis, I always call it the Horn diagram, and I don't know what the people from CWR call it. And once again, we have, you know, one parameter on the y-axis and another one on the x. And here, it's 1 over the Wedderburn number. And here, it's the mixed layer depth over the basin depth, and it's probably really the mean basin depth. But remember, they're doing all the work in in a channel that's like this, and so it doesn't have bottom topography, so there's some extras in there. But what they did through all these experiments was figure out the case when you would have linear waves, types of waves called surges and solitons, internal bores, and then a type of motion called a Kelvin-Helmholtz billow, where because of the shear, the velocity gradient at the interface, the water just rolls up and spins on itself and then collapses into patches of mixing, okay? Now, a little bit of scaling, if we have 1 over W, well, here's 1, so that's that case of a full upwelling. So as it gets bigger, now the thermocline isn't just upwelling to the surface, it's going even farther, right? It's a really big tilt. And this number, I think, is around 0.2. I don't know if my math is going to be really good over this morning. Today I can't tell you if that's 10 or 20 for a Wedderburn number. Some days my math is really great when I look at things. But in the next, I'm going to show you examples of some of these types of waves, and then how we can start to think about them in an ecological context. And then after we look at some of these movies of waves, then I'll compare dynamics in 2 small dimictic lakes at different latitudes. And in one dimictic lake, in a cold versus a warm summer. And then we'll see how the time goes, because I know there's some people who'd sure like me to talk about some of the polymictic lakes, and I may or may not get there, which is why we may want to meet tomorrow, as well as some of this other data. But let's keep going. And another goal is, if we have this internal wave regime diagram, can we link any ecological processes to it, including quantifying the coefficient of eddy diffusivity? So here's the first one. This is the surge and soliton regime. The thermocline was tilted. This is the surge. Those are the solitons. And you see how they break in the near shore. And we'll watch this one more time. And this is some numerical modeling done by Kevin Lamb, and it's based on those flume experiments of Leon Boegman. So the surge, followed by the solitons, and now, depending on the basin slope, they will break and they will mix. And now, as ecologists or limnologists, we can go, are there nutrients here? Are they dissolved gases? Are they going to come up over here on the boundary? Okay. And that's actually one of the first papers I worked on once I understood this process. And the mixing was more at the boundary, but there's a lot more work to do with that. Now, the next regime is a bores and billows regime, where the Wedderburn number is less than 1. So again, Leon and David Horn did great lab experiments, but the modelers got super interested, so then they modeled it. And so this is modeling by Stashek, Lysenko, and Hutter. So now, once again, remember up here is where it's turquoise is the water that's less dense. Oh, my mouse has disappeared. And the purple is the denser water. So the surges, I can't point anymore, guys, sorry. The surges are those more steeper features on the side, and in the center, you can actually see then the roll-up of these Kelvin-Helmholtz billows. And then it keeps going, and they get bigger, and then I probably clip the rest of the movie. But the idea is then you really get a lot of intense mixing across that thermocline. And if you remember when I showed you that data, the time series from Toolik Lake, and the thermocline was like this, and then went woof, down, right? That was a time when that process would have occurred. And we call it internal bores and billows. We can call it a hydraulic jump, okay? So why do we care about these breaking internal waves or nonlinear internal waves? They cause turbulence. They're the dominant mechanism for vertical exchange in the pycnocline and hypolimnion. As the Wedderburn number becomes smaller, the probability of wave breaking and formation of Kelvin-Helmholtz billows increases, and the eddy diffusivities increase. Now, let's take a little time so that we get more used to this term. It's a transfer coefficient used to calculate fluxes of heat solutes and particulates. The molecular conductivity of heat is 1.4 times 10 to the minus 7 meters squared per 7. This is one of those numbers you just always memorize, okay? And for some reason, I always like to tell you what the typical KZ is in the ocean thermocline, even though we're working in lakes. And it's on the order of 10 to the minus 5 meters squared per second. And these little things right here are meant to represent turbulent eddies spinning around, because the concept of the eddy diffusivity came from the kinetic theory of gases, with gases kind of spinning around. Okay, and it's kind of neat because a simplistic relationship for KZ is simply the velocity of coefficient C times the velocity of these eddies and their length. And this would be more of an RMS length scale. But it's neat because once I felt confident enough to do that for the upper mixed layer, I began to calculate eddy diffusivities for the upper mixed layer. Now I have some fancier ways, but this is a really good start. Now, another thing I always think is super important is to memorize reasonable values of eddy diffusivities. And as a physical limnologist, that's one of the things we do. We just know numbers. Oh, that's really mixing a lot. Oh, nothing much is going on there, okay? And the epilimnion, which is more weakly stratified, we expect those numbers to be from 10 to the minus 5 to 10 to the minus 2. The thermocline, which is more strongly stratified, we might think they're 10 to the minus 7 to 10 to the minus 5. And the hypolimnion, which is more weakly stratified, they could be 10 to the minus 7 to 10 to the minus 4. So again, the molecular diffusivity of heat, 10 to the minus 7 meters squared per second, but salts can be 100 times less. So that might even help explain why we can see more in a time series of oxygen than we might actually in the temperature, okay? Alrighty, and one more little goodie about these, besides saying that I don't know if you can see that, but it says these are ballpark numbers. We have to calculate them for every case. But another thing that you can, oh, actually I'm ahead of myself. Just to give you more sense of what we mean when we talk about an eddy diffusivity. If you put tracer here at 20 meters, and my little pointer is trying to show you a plug of tracer that you put in an experiment, and then you went out 3 days later, maybe have a fluorometer, you're using rhodamine, you can see that the concentration is spread. And then maybe 10 days later, it might look like this, okay? We characterize that change, with an equation like this, and here it's in velocity, but here really should be concentration. But that's what the eddy diffusivity is giving us a feel for. What's the spreading? And the spreading is probably too gentle of a term, right? But when we think about a tracer, they spread, okay? But it's the mixing caused by the breaking of nonlinear waves, shear from currents, and in the upper mixed layer, and even sometimes you can get an instability in the thermocline. And Andreas Lorke wrote a very nice paper on that. So there's a lot of mechanisms to cause the turbulence. Now here's another tool that you can start to bring into the study you might be doing at an ecosystem level. Because if you say you can calculate what we would call a time scale of mixing, and you think about the units, right? Because L squared is meter squared and KZ is meter squared per second. When we do that division, we end up with time. And here I've given you some numbers. If the thermocline was 10 meters and that eddy diffusivity was 10 to the minus 5 meters squared per second, it would take 100 days to get a flux across the thermocline. Now, if it was 4 meters, the time scale could be 18 days. And if it was 2 meters, it would be 5, right? So you can see how really important it is for this number to be high in order to have actually much flux across the thermocline and much transport of whatever's in that hypolimnion up, okay? Now, again, this is when we're dealing with, if we had a big cooling event, right? And in this lecture series, I can't talk about cooling, there's not enough time. If you had a big cooling event, all that instability because of the cold water near the top sinking and causing mixing, that might be your mixing agent, and you might have a different time scale. So keep that in mind. There's different ways, but this is your ballpark for across the thermocline. So one of the things I did was to say, okay, what do we know about some lakes and where they might fit in that regime diagram? So I took some lakes that I know, and some of them you're going to know. And if you look at the side, you go, aha, Tanganyika. Here's Tanganyika. And remember, this is the 1 over W. So we can have a tremendous amount of upwelling in Lake Tanganyika. I don't know about Lake Kivu, Janvier, I'm wondering. Then we have the long, narrow lakes that some of you are all familiar with. And data there showed regimes like this. And here's Loch Ness. And then in New York, we would have Seneca Lake, right? Also in New York, Cayuga Lake up here in this regime. Don't know why they're different, but I think it has to do with when people did the study. But these are the lowest values that have been recorded in these different lakes, okay? Here's Tulip, for which I'll show you some data. Mono Lake, which I've studied a lot. If we have a chance, I'll get a movie. E5, for which I'll show you data. It's a small lake in the Arctic, as is N2. But the lakes in which people did some of the very first metabolism experiments were these ones where the internal wave types are these nonlinear ones. And these are Peter and Paul. And in the northern temperate lakes, it's Trout Bog. And then in southern Michigan, where Bob Wetzel did his work, this is Wintergreen Lake and Lawrence Lake. So remember, in terms of the records that I've been able to see of a fairly long time series, were based on compilations that were done by David Horn. And then later, I think Leon Boegman did some too. These are the lowest values seen. And then we could still ask, well, how frequent do the low values occur? And does it affect the stratification, right? And what does it mean for nutrient supply, right? So those are some questions. But one of the things that I did is I just made this schema for generalizing between lakes and over time. And the one is biotic processes are going to dominate nutrient flux across a thermocline if the Wedderburn or lake number is greater than 10. And then two different regimes for the one where we can have the combined processes. One where the regime is sort of between, or the Wedderburn numbers between 1 and 10, and one where it's much less, okay? And then I've just got little schemes. Here's our breaking internal wave, but never forget biology. Here's our migrating zooplankton. And then over in the other lakes where the biotic is critical, when we have the migrating zooplankton, and we can have migrating fish. So you never want to forget it isn't all about physics, or it isn't all about biology in terms of nutrient supply. So now I'm going to give you a little comparative data with Lawrence Lake, representative of small sheltered temperate lakes, and E5, which is an Arctic kettle lake, similar in size. It's not sheltered, and it has a much smaller temperature gradient across the thermocline. Okay, so this is the kind of graph that we make a lot in my lab. And we've got a time series, and it starts around April. And again, because we use MATLAB, everything is always in days of the year, and I'm not super fast with all the date conversions. So then later I look them up on a NOAA guide. Okay, this is around the 1st of April. This is around the 27th of October. The upper panel shows a time series of, it's actually lake number, because it's easier to calculate on a computer, okay? Wedderburn number takes a lot more difficult programming because how you calculate that change in density over time is much more complicated. But what you see is, right in the beginning in spring, shortly after ice off, there's some low values, and then they go up, right? And this is 10, and here's 100. And you can see that in the summertime, those values are really not going below 10. And then we get into fall and they begin to drop, right? And now you look at the stratification. Temperatures 30 degrees for the high, around 5 degrees for the low. We see this here. We see spring warming. When this lake is stratified, it has a little diurnal mixed layers. I'm pointing these out. I know it's hard to look at these, especially if you're on a laptop. But you basically notice, let's say the mixed layer here might have been about 3 meters. All the way down to the bottom, this lake is stratified. So it's basically all a metalimnion, okay? And there are some internal waves, right? You can see these little things right here, right? But it's really a really stratified lake. And by the way, the attenuation coefficient is about 0.2, so the aphotic zone reaches to the bottom of the lake. Okay, these are the eddy diffusivities. Okay, and we do this by a heat budget method, and there's not time in this talk to go through all these methods. And then the KZ for the upper mixed layer, I do with that simple turbulent velocity times the turbulent lane scale. But you can see that the only time you have any mixing is due to the heat loss at night, right? So you stratify in the day and you mix at night, and you stratify in the day and you mix at night. So this kind of lake, which is a classic one where, like I said earlier, a lot of metabolism studies were first done, and the sensor would have been at 1 meter depth. You can see there isn't going to be a lot of flux from the lower water column up to that oxygen sensor, okay? So in a lake like this, the biotic interactions determine the productivity. There's also some groundwater intrusions, okay? And they supply, some nutrients down here in the lower water column. But layered communities develop, like there was a layer of cyanobacteria here and a layer of purple photosynthetic bacteria there. So very still, a lot of theory, predator-prey interactions was developed in lakes like this one, and the metabolism calculations are really simplified. Then you shift to the Arctic. By nature, that the air temperatures are going to be colder. So this is the same kind of graph. And we've got a time series. It's really lake number, but I called it Wedderburn number to keep it simple for the lecture. The dotted line is 1, right? So look how frequently we have events in that lake where you have full upwelling and then even more upwelling to the surface. And look at the difference in the patterns for thermal stratification. And the uppermost temperature I put here, which I don't even see, is 20, and the lowermost is around 5. So a few times with a little warming to maybe 14 degrees. But the thermocline is much thinner. It's a real thermocline. And then when the lake number went down, and of course it got colder, see, it got thinner. And then when that lake number went back up again, notice a secondary thermocline formed, which isn't something I usually talk about. But this is a strong secondary thermocline. Then we got into the Wedderburn number dropping down probably even a 0.1. And now you can see, well, actually you can see it here and you can see it here. You can see that big thermocline jump that's telling you there's been a lot of exchange of cold water from the lower water column and some warmer water from the upper water column, really intense mixing with it. Billows and bore regime. Very, very dynamic. So the eddy diffusivities here look completely different than what we just saw for Lawrence Lake. In the water column, you can see, the thermocline sometimes is molecular. There's a lot more mixing near the bottom. Here's a case with more mixing on the bottom. In the upper mixed layer, the eddy diffusivities are much, much higher and over a much, much greater depth. So you can see that this lake is much more dynamic than Lawrence Lake. Vertical exchanges are across the thermocline are by this internal wave-induced mixing. Layered communities do occur sometimes in here at the start of summer, but they're going to be disrupted, and the time scale of mixing would be hours to days. It would probably have been 100 days it was all molecular in Lawrence, so there just isn't one. Okay, does that make sense? Does anybody have any questions about those graphs? But it gives you a real sense of how really different lakes can be. And I haven't actually yet seen any Gleon papers that take advantage of this kind of knowledge, which has been around for a long time. And I could see some very nice Gleon projects developed, because many papers now, they get like one oxygen profile or one temperature profile and do long time series. But if people want to band together with their data from lakes of different latitudes and work with your time series data, you're in a setup then to do some really interesting comparisons. Okay, so summarizing that, 2 lakes, same size, different latitude. Lawrence Lake During the stratified period, the lake number is always greater than 10. Mixing in the surface layer is dominated by heat loss and wind stirring, and mixing below is at molecular rates. E5, the lake number frequently drops to 1 or below. Mixing in the surface layer is caused by heat loss, wind stirring, and shear at the base of the mixed layer. And the turbulence in the meta and the hyperlimnion is induced by internal wave breaking. So real different. And probably I've really said this, looking at my clock here. Lawrence Lake, the biotic processes are so critical for the vertical fluxes of, let's say, nutrients. And in E5, the abiotic processes also contribute. I'm going to show another example like this, but start to think about oxygen. In some of the recent papers that came out showing that lakes are becoming more deoxygenated in the lower water column. The upper one because of warming, but the lower one, probably land use change. And think how if you use these types of scalings, you can begin to go, oh, this is why this one became more deoxygenated than that one, because now you've got a dynamic tool that allows you to do more interpretation. Okay, a little bit more up here in the Tulik area. I'm going to show you a difference in the mixing in cold versus hot summers. Nicely here, we've got a map. You can see in Alaska, Tulik Lake, a multi-basin kettle lake, maximum depth a little over 20 meters, and two, maybe we'll get to it, even smaller, 2-hectare lake, 150-hectare lake, Tulik in summer. So this is a similar data to what you just looked at, and this is how you get your eyes trained. You have to look at data like this over and over and over, and then you begin to see patterns and you begin to be able to make interpretations. But in Tulik in the cold summer, here's this lake number, Wedderburn number of 1. Here it is at 10. And just like for E5, because the data is from the same summer, many events when the lake number goes low, so we would expect a lot of tilting of that thermocline. Temperatures, again, scaled like the other figure, 20 to 5, a couple warm fronts. Thermocline, the way I drew it, it's not as stratified as E5, but it might be. The thermocline here gets super thin when this lake number drops. So now if we do calculate a coefficient of eddy diffusivity, we can get flux through that relatively fast, okay? And here's the time series of eddy diffusivities. Again, the scale, almost 10 to the minus 3 down to molecular. And the thermocline, you can see that there's some flux through the thermocline all the time. Definitely higher Kz on the bottom. And then once again, the mixed layer is very dynamic. So think about light supply to phytoplankton. Are they getting mixed below the euphotic zone? In this lake, no, the euphotic zone is about 8 meters deep. But when you have this type of time series of eddy diffusivities, you know, like for your own lakes, you can begin to go, oh, how fast are we moving the phytoplankton around? How fast are the zooplankton being moved around? You've got a lot of power to interpret the biology. Now here's the warm summer. And now you'll see why I scale between 5 and 20, because in the warm summer up at Tulik Lake, you can see that the temperatures did reach about 20 degrees centigrade. But here on this time series, and for once at least I've got the dates right, June to mid-August, you can see right after ice off, they're kind of low. And then in this summer, the values were sort of hovering around 10. Occasionally they went a little bit below. So it's, you know, it's not as extreme as Lawrence Lake where they're up above 100, right? They're dipping below 10. There's a little bit more wave activity, but it's radically different than the cold summer. It's like a regime shift. But up at Tulik, we're not having a steady shift in regime, but people working in some lakes where you're seeing a steady increase in heat content over the summer, you might, with calculations like this, be able to see what's the difference like that causes flux between the upper mixed layer and the water below. But here's the eddy diffusivities. In Tulik, then in the warm summer, through the thermocline, very much in contrast to what you saw in the other picture, It's often at molecular rates, very little exchange. So a summary, warm versus a cold summer. The warm summer had fewer clouds, it was less windy, and the lake number was more or less greater than 10. Thick thermocline, high eddy diffusivities, the primary production was low. The cold summer was windier, and the lake number was often below 3, and in fact often below 1. A thinner thermocline, lower eddy diffusivity, plus upwelling. And the primary productivity was moderate. The phytoplankton were diluted, and for the zooplankton, they were also mixed, so grazing was more difficult. So these dynamic conditions, they really set up between year and, of course, between lake differences. Okay, so what I did here is rather than jump into some summary slides, I thought I'd put you all to work and show you some data, okay? And it's some time series temperature and oxygen data. And I want you to tell me a story, okay, with this data. And I, probably need help of Tag and Freya if she's still here. But we have, once again, a time series of temperature, and this is Toolik Lake in 2017. But since many of you are studying metabolism, I've included the dissolved oxygen, which we measured with mini dots. And here you can barely see it. All those black dots show you how many thermistors we had, and this shows you how many mini dots we had. And then in the lower panel, we've got percent saturation. Okay. And again, I didn't make a quiz. There's a way of making a quiz for you all to take. But, and I almost wish you could jump into different breakout rooms and talk to each other, but that may be too hard too. But look at this data. And I don't know if you just have this black bar at the top like I do. You see a warming period. You see it's getting cooler. You see it's getting cooler. It's the Arctic. Summer doesn't last very long. Are there any times in that graph where you might think that the lake number actually dropped down to a value near 1 or below 1? Did it happen any time in the summer? Because remember, we haven't talked about fall cooling, and I haven't talked with you about convection, right? So you could say, oh, Sally, the thermocline deepened here because the nights just got colder and there was more heat loss, and it mixed for that reason. You could tell me that, okay? Because I haven't been teaching you about energy budgets, and I haven't shown you any of that kind of data. But one thing to keep in mind is that when you work in the Arctic, and the temperatures of the water are cold, and by here it's about 10 degrees, evaporation becomes much less than you might have in a temperate or tropical lake at the same season where the water temperatures are much higher. So you don't have necessarily as much deepening from convection. And that's one reason why here these upper mix layers are so small, right? Because there's just not that much heat loss at night, okay? Anybody want to make a guess, like when there might have been a time when that lake number dropped down around 1? And I might need Tag's help because I can't see everybody. Does anybody have a hand up or want to hazard a guess? Melissa, do you? Since you may not have seen this graph before, but you've had a few more lectures on this topic. Okay, so nobody, as far as I can tell, nobody's willing to make a guess. Well, anyhow, let's not answer that yet. Let's look at the oxygen, because this is kind of like really crazy. If we look at this oxygen, okay, so you have to always remember, like, around how cold the water is. This is 10 degrees, and what saturation is. These concentrations that you see at ice off are actually really pretty high at 10 milligrams per liter. Some of you working in hypoxic lakes, you know that's high, okay? And so if you see We have this stratified layer here, and I will tell you there's going to be a chlorophyll maximum there. And if you see this increased oxygen there, do you assume that that's because of primary production? I want to assure you that the first time I saw any graphs like this, I was assuming that the high oxygen values were associated with the growth of the primary producers, okay? And it's been always interesting because this feature of higher oxygen at this depth in thermocline is in almost all the Tulic data, and always right around here. Look, I didn't put any dates for you, so this is the end of June, and this is now towards the end of September. Always around here, which is in early July, the chlorophyll maximum gets mixed away. Right? Something happened here in this thermal structure, and all of a sudden we don't see that peak in oxygen. Okay, so that's a question. But now let's look down here. What's happening to the oxygen in the lower water column? And I told you the aphotic zone in this lake is 8 meters deep. Okay, so we know there's not going to be much photosynthesis there. So what is this data telling us is the dominant metabolic process in the hypolimnion? Does anybody want to say the words I know many, many of you who are listening to me know? All right. But I can't see any hands raised. I don't know, Tog, if you can, and I'm not sure if Freya is still here. Right? This is that symbol of respiration, right? So the bacteria, is it the bacteria in the lower water column, or is it the sediments at the bottom are drawing down the oxygen? Okay. And then while this thermocline was fairly thick, and I don't even know if I made a graph of it. Well, I do have a graph of eddy diffusivity, but I didn't look at it yesterday. While this thermocline is fairly thick, this region is isolated, right? So you're just having this steady, steady drawdown. And so, we say that's net heterotrophic, okay? But now what happened? The oxygen here was around 9. And then the oxygen, it went up to maybe 9.5. And now the oxygen has gone up to 10, right? And the anoxic water has gone away, right? So why would we have less oxygen down here, and then all of a sudden it looks like there's a whole lot more oxygen? Does that make sense, right? But to do this, right, because you would think, right, we can tell from the temperatures that we've had a mixing event, right? And so we've mixed up this water with lower concentration, and you would think that in fact the concentrations would go down. Okay, so now let's look at percent saturation. And this was like a showstopper for me when I've only done this for about 3 years of data. And all of a sudden you go, oh man, you can't interpret oxygen data unless you also look at percent saturation. Because now, instead of just having this little maximum here in the thermocline, you can see that the percent saturation up near the top is above 90% early in the summer. And in my class, I would have wind speed at the top, and you could see when it was windy and when it wasn't. But here, probably the periods when it goes up even more are times when it's not windy, and then we don't have gas exchange across the air-water interface, okay? And so now an increase, you have to, again, for those doing metabolism, you have to think really hard. Is that increase because of productivity, or is it simply a slowdown in the loss of oxygen across the air-water interface? And then there's no explanation for this high peak other than the fact that the water temperature was colder, right? And we see how the oxygen percent saturation decreases through the water column. Now, over the summer, instead of seeing an increase as we see in the actual oxygen, as we look at that percent saturation, see how it's really decreasing. And now, when we get the mixing event, see how percent saturation went even lower. It's below 80% for the whole water column. Okay, and then it does increase again later. Right? So again, to summarize, and you guys, I know these are recorded, but I think this is a really, really interesting graph to think about oxygen dynamics. You need to know the percent saturation. And, you know, the lake number did go down to about 1 here. We did have a big full thermocline upwelling. And at this point, you entrain that hypoxic water, and the percent saturation goes down. But because the water got colder, right? Because there's cold water even below my sensors, right? So the overall water column got colder, the saturation was higher, right? It could hold more oxygen, but in fact, the percent saturation is lower as that was mixed up. And later when we see this increase, it's simply because now you've got the whole water column, those lake numbers are super low. The whole water column is exchanged with in contact with the air-water interface, and so oxygen can come in from the atmosphere. So again, for those of you who are actually studying lake metabolism, I hope that going over this graph is actually helpful in how you need to be thinking about what are the physical processes that are occurring. And it's not only oxygen, it's also being really careful with the percent saturation so your interpretation is not confounded by the fact that water of different temperatures can hold different amounts of oxygen. Now, one other little goodie with this figure is I say, were there any stream inflows? And here, you have to go back and look, is there anything anomalous in this time series temperature data? And I have to tell you, I'm watching our clock here. This was actually a storm event that brought in a bunch of water from the stream. And over here is another storm event that brought in water from the stream. And over here was another one. So during COVID, when I couldn't have my lab class outdoors, we actually took this data. You know, I had made this for an exam before Melissa might have even had it. But I'd used this before. But we took this data set because I knew it was a good one. And we got all the data from the stream inflows, the discharge, the CO2 in the stream, the CO2 in the lake, the DOC in the stream, the DOC in the lake. And we could actually see when the primary productivity went up as that stream water came into the lake. So it was a really, really wonderful opportunity to learn more about the connectivity between streams and in the receiving lake. So look, now we're at I'm going to do this slide, and I think I'm going to do the next, and then we have to make a plan, okay? And so it's really important to have this really critical concept in mind. And up here, I think it's hidden, critical concept, 1 versus 2-dimensional. So often we think of our lakes as 1-dimensional. And we think that eddy diffusivity that I was talking to you about is going to tell us about whether or not we properly have vertical exchange. But Mortimer's beautiful graph, once again from Windermere in 1949, showing this strong upwelling, in a case like this, we say a lake is 2-dimensional, right? Because it's not like we're just mixing straight through a thermocline. We're really having mixing that's coming from the hypolimnion right to the surface, and then mixing up here. And as I showed you, there's a thermocline jump. The 1D models, like there's a lot of people within GLION and a lot of people worldwide using 1-dimensional models, but they may not capture this kind of extensive exchange. And when I calculate the eddy diffusivities, I use a technique called the heat budget technique. And again, it's an old one. It goes back into the 70s when it was developed. And even that method may not be right. So I'm telling you this because you've got to be really careful if you go, hey, I'm going to use GLM, I'm going to go model my lake. If your lake has a lot of events with these low lake numbers, those models can't really capture that mixing. And it may be the one that's really setting up the conditions, like in Tulik, it dilutes all the phytoplankton. And so the productivity is going to go down. In other lakes, the more classical one is that's the time when those nutrients come up. And that's the time that your productivity is going to increase, right? So it's really important to remember that as this dimension goes down, you shift from a one-dimensional paradigm to a two-dimensional one, with those dynamics extremely hard to capture in one-dimensional models. And it's even hard in the 3D models. And this other one, this might be a little esoteric, maybe I shouldn't stop here. But in some of this data, you saw especially in Balbino, you saw the diurnal thermocline above the seasonal one. And this one, I got to tell you, I have a paper that came out in 2009 where working in Mono Lake, and I calculated a Wedderburn number and I calculated lake numbers, and they were different because Mono Lake is a salt lake or alkaline saline lake. So it's got a chemocline. And I'm going fast. Sorry for those of you who don't know those words. But the upper water column was distinct from the lower one. But recently I was doing a paper on a small lake in Sweden, which would have been in between E5 and Lawrence Lake. And I couldn't get things right. So I went back to Monosmith 1986, which is such a good paper. And I realized I really had to have a Wedderburn number for that upper diurnal thermocline, because what I was learning from the lake number was that lake shouldn't have had any vertical exchange. But because we had lots and lots of profiles of turbulence, I knew it was occurring. So I realized my lake number might say, okay, your thermocline's not moving, but the diurnal thermocline, which is encompassing the whole upper part of the lake, is moving. And in fact, over at the boundaries, it's stretching the top of the metalimnion and can allow some leakage around the edges of water from the thermocline into the upper water column, where it can then shoot across in that circulation. So things can get a little harder. Now let's see what this next slide is. Look, it's a movie. So now we've reached this break point. Should I continue and show you all a few movies, or would you prefer that we just start again tomorrow morning? And if you wanted to see a couple of movies, I think I could wrap things up in 15 minutes. And if you wanted to meet tomorrow, I knew that some people here were very interested in horizontal exchange. So I began to think about how would we think about horizontal exchange and not just vertical, okay? And it would give time for a bit more discussion. But I leave it to you to decide if I should just keep on going for a while or if we should convene tomorrow. And Freya suggested maybe people should raise their hands. And I can't, with me sharing my screen, I can't look at everybody. I don't even know if I can go to gallery view.
Yeah, no, that's, yeah, we could use, with the reactions, we can kind of, so with the reactions, there's like a clapping emoji and a thumbs up. And if you want to continue for 15 minutes, we can do if you want to do the clap, and then if you want to do tomorrow, we can do the thumbs up emoji if people are just kind of a quick way to kind of poll the group. So okay.
Good luck. I said, with my screen shared, I sure can't see anything.
Okay, someone just doing a tick as well, just to. Okay, so it looked like there was a peak of people looking for you to continue for the next 15 minutes.
Okay, so, that's great.
There's also people interested tomorrow as well, so we can keep going for another 15. Okay,
and then if anybody wants more interaction with me, maybe we could just set up a private Zoom call at some time. Okay, I'm more than happy. So look, some of my colleagues, I've mentioned Leon Boegman, and his graduate student was Dorostkar, whose first name I know, and I'm blanking right now because I haven't thought about it. Dorostkar was absolutely thrilled when he began to be able to make these movies, because it hadn't been done before. And he used a 3-day hydrodynamical modeling. He was using MIT GCM. I was like his external examiner, that sort of thing on a committee. Beautiful, beautiful work. So again, as you saw with the Ben Hodges movie, we start with an upper mixed layer and a thermocline and, a hypolimnion. One of the features that sets Cayuga Lake apart from many others is this sill near the bottom. Oh, and for those of you who don't know all the lakes of the world, Cayuga Lake is one of the Finger Lakes in New York State, and it was glacially formed, and it's very long and narrow. And these lakes are the first ones where the nonlinear waves were discovered. Hunkins and Flegel, I think, in 1973. I think it was their paper. But anyhow, let's let you all watch what's going on with this thermocline as, in response to the wind. You can just totally see. I mean, look at the magnitude of the excursions, that actually occur within that thermocline. They're huge. And Leon also gave me movies of some of the velocities, and they're ripping. They're 20 and 30 centimeters per second going across that lake. So if people are interested in like that methane problem, is it produced near shore versus in the thermocline? When you have some of these models, and if they give you realistic current speeds, you're in a position to start to think about how much horizontal exchange really occurs. Now, I also, for those interested, I recommend reading this paper. The eddy diffusivities, right? At periods I'm going to try to capture one, like right here, the eddy diffusivity through that thermocline actually goes to 10 to the minus 2 meters squared per second. It is, it's short, but it's really a time when you can have a huge pulse of material going through. So once again, the lakes can be so incredibly dynamic. Okay, Mono Lake. This is a lake that here at UCSB, we began to study it in the late 1970s. There's a long story. Let me not get carried away. But I had a very, very gifted postdoc who modeled the lake. And this one, okay, there's so much information, he couldn't even save the full model. But when the wind is strong and we have changes in wind direction, okay, we're going to have to do this twice. Here comes a pulse of wind. Watch how all the warm water gets pushed over to the northern shore. The wind relaxes, it rotates around. Now the wind is coming up again. You see the water going to the northern shore. And then as it relaxes, right, you can see the eddies. Okay, I'm going to do it again. This one you can tell I couldn't control very well. And it's really a shame. Computers have improved since Javier made this movie. Notice, so the strong winds coming off the Sierra Nevada come this way. But notice when I show this again, that the warm water goes here and the warm water goes there. Also, if you watch the wind direction, here the wind is high and then it changes direction. Then we have a lull and then the wind is high and it doesn't change its direction as much. You're going to notice that this water rotates.
Sorry, Sally. We can't see the movie. Sorry, we just
you can't see this movie.
Yeah, we just see the bathymetry map slide.
And you don't see it now either.
No.
Oh, isn't that a shame? Yeah.
Is it? Okay.
There is a solution. Okay. I'm going to go a little bit farther and then I'll step back and I'll go outside of PowerPoint because I can play it outside the movie. It's showing beautifully to me. But thanks for telling me. Oh, look at this. Guess what? It took over my whole computer. So then I couldn't. All right, now let's get this. Yeah, I tried to get real creative and figure out a way to make more movies work. And then the new software changed things even further. Hold on a second. Okay, I'm going to jump to another movie, and hopefully this one will show. Okay. All right, now we're back. Okay, can you see this? Do you have my, yeah, and this is another embedded movie, so I hope it shows. Can you see things changing here? Okay, let's go back, and I'll start it in a minute. The upper panel is wind speed. The lower one is wind direction. This lake is Lake Pleasant in New York State. It's about 4 kilometers long. Not that it matters, it's got a little island here. We set up an eddy covariant system at this location so that we could quantify CO2 fluxes. We also had, we did a whole lot of turbulence profiles, and we had thermistors, so we could get lake number and parameters like that. We also did synoptic sampling, for CO2. But what Javier Vidal did is he's modeled the lake, okay? So we're starting in fall. You can see that already there's been a lot of deepening of the mixed layer. Yeah, and there's just a few little dimples on the bottom, which have cold water. So this side is going to show you temperature. Here, now you're going to see the surface PCO2 concentrations. And at the start of the movie, there's very low concentrations, although still above saturation, in the epilimnion. And then they are much higher. And in order for this movie to tell a story, we had to set the scale bar so you can't really see the numbers, okay? But they go above 6,000. And remember, atmospheric is around 400, 440. So let's watch the movie and see what we can see. And unfortunately, the prevailing wind direction is kind of like this, right? So you can see with the wind, see how that warm water is pushed across, and see where the CO2 is upwelling, okay? So you might see it upwelling along the length, but it was upwelling over here, okay? Now again, here comes some more wind. The warm water is blown here. The upwelling of cold occurs there. There's the CO2 coming from the hypolimnion and spreading. And notice how discontinuous it is. Think if you're doing CO2 studies, how you've got to be sampling with a lot of chambers or have eddy covariance. All right, again, let's see if we get another burst of energy. But you see, all those types of waves I was telling you about, they're captured in this model. Okay, the wind is going to pick up again, although not as high as before. We get some more upwelling, okay? And we can see how little of that upwelled water even makes it into this basin where we had our CO2 eddy covariance system. We didn't know that when we set up the experiment, right? Which is why sometimes people model lakes before they do experiments. Okay, does anybody want to see that again? I'm thinking about what else I have to show. But it gives you a sense of the spatial variability of upwelling, how sampling at one location in a lake can be terribly misleading. And again, the connection between the internal wave motions and Wedderburn numbers for flux, okay? And, this is just a fun picture I put in. This is your sage. And this, of course, is that breaking of waves along the boundary. Okay. Alrighty, I'll show this one. Here we have Lake N2, a small lake up in the Arctic, right before ice is coming off. And it's just a thin, thin, thin sheet of ice. Well, for fun, sometimes even in tiny lakes like this, we put out a whole lot of thermistor chains. these are things where I just said to my postdocs, oh, instrument the lake however you want. I didn't guide them because sometimes it's really super to let somebody else's creativity be what matters. So they did. And then my postdoc, Alicia, did a wonderful job of making all these figures. But these are the locations of our thermistor arrays. And then we had a couple on the lateral side. The data start at 2 meters and they go down to the bottom, which is around 10. So what you can't see here is the fact that when snow melt came into the top of this lake, that water was very, very fresh. And the lake itself doesn't have a very high conductivity. It's around 200 microsiemens, but the snow is 20 microsiemens. So at the cold temperatures around ice, where the temperature density curve is nonlinear, conductivity makes a really big difference for your density stratification. So right underneath the ice, with that fresh water coming in, it got warm. And if you look at the scale bar, here's 4 degrees. In fact, some of it probably even got up to 8 degrees. And then over time, you can't see what's going on. And now the ice went off and the wind came up. And you can see how the warm water was just immediately pushed to one side of the lake, and we had upwelling over the other. Wedderburn numbers less than 1. But down here is anoxic, and it's full of methane, okay? And some CO2, but that's above. So we push in the heat, right? And you still see an upwelling an hour afterwards. And then the thermocline leveled off. And it's kind of interesting because you can actually see that the hypolimnetic water ran up the side margin of the lake. And then we got another pulse of wind, and and the thermocline downwelled again, and then this hypolimnetic water ran up the other side of the lake. Alicia also made a movie on this, which is the kind of thing you can do when you've got, when you're really good MATLAB. I don't know if an R can do this, but MATLAB can take this time series data and make incredible movies with real data. But the importance here is that, think about you're doing a study of CO2 fluxes. Because the mixing with the Wedderburn number less than 1 was so intense, all this heat got mixed down, and it didn't allow the ventilation of the lower water column. So you retained anoxic conditions, which is a setup then for anoxia in the lower water column even in summer, and then some of the methane is retained. So very, very important when you want to do budgets for CO2 and for methane to understand these processes at ice off. Okay, and now I'm going to stop, and I know, for instance, that if Sam is still here, she'd really like me to show this data from Lake St. Augustine, but most of you want to call it a day, so I won't. And I want to, oh look, hold on a minute. I'm going to go through this at blitz speed to tell you a sense of, okay, we had stories here with Lawrence Lake, and Tulik was in this case, and Tulik and Cayuga were there, and some of the others were here. We can map our lakes into these different regimes and then come up with schemes. Oh dear. I can't tell, guys, I can't tell if I'm still connected.
Yeah, well, we can't see your screen now.
Yeah, that's what I thought. Darn it all. So I'm trying to pull it together, knowing that some of you need to leave.
Yeah, we just have a question. Sally, I have a question in the chat. Ben, I'm wondering if you'd like to maybe ask Sally your question.
Okay, thank you, Sally, for the presentation. Really, it's a great talk. My name is Ben, and
okay.
For my PhD, I've been studying about the thermocline, and from what you've definitely shown, it shows that even in a day, in the course of the day, the thermocline is very, very variable. It keeps moving. So I'm just wondering, which advice would you give in case someone is interested in targeting, because in case your sampling is targeted onto the thermocline. then what advice would you give to target it? Because it shows even in time, after an hour, it's moving. So
Well, I guess you got to use these dimensionless indices. Ben, are you going to be working in an instrumented lake?
come again?
Are you putting thermistor arrays into the lake you'll study?
So what I'll be doing is I'm studying lake at Lake Steckling, and I'll be doing a couple of things, but I'm looking at microbial degradation within the thermocline, but also I'm targeting the thermocline, but I have to sample above it and below it. But from this, it shows that it's really very versatile, and I'm now going mad on what time should I do the sampling, because even in an hour, it's moving.
Oh, sure, but look, yeah, you know, it's pretty interesting that, but I need to know more about your lake, and I need to know more about what instruments you have to answer. Is it a big lake or a small lake? You might have said it, but I might not have heard what you said.
It's quite a big lake, I would say. In Germany, it's quite a big lake.
Oh, you're studying a lake in Germany.
Yeah.
Okay, and then does it have time series temperature measurements?
Yeah, it does have there's
Yeah.
profiling which is being done on a daily.
Okay. Well, look, like I work at the same location as the Arctic Long-Term Ecological Research Project, and they routinely take samples like right below the surface at 1 meter, 3, 8, 12, and 16. That's routine. So when you have the time series of samples and you have the time series of like temperatures from the instruments, then even though the thermocline is rocking, you know from the time when you took your samples what its position was. And you know how it was changing in the days before. So you're in a position to say, okay, it was stratified, it was just behaving normally, or my goodness, I just captured before and after a storm event. Now I can see why the primary productivity's gone up, or now I can see how come the chlorophyll either increased or decreased. Does that help? So when you have the background on the thermal structure, then you're in a position to interpret that, you know, biological and chemical data just that much better.
Yeah, it does help. Thank you.
Okay.
And then Ulrika, I think, has her hand up.
Yeah. Hi, I'm Ulrike Overteker from Italy. And could you explain in more detail the relationship between evaporation and the not much heat loss at night in cold water lakes such as Tulik Lake? So you said that there is not much evaporation, therefore there is no high heat loss during night, but I did not get the connection. When we do the calculation for evaporation, we're including like the temperature gradient in the temperatures. This is the kind of thing where I'd be much happier if I was to send you the equations. And I just keep as a rule of thumb, from cold water, the evaporation is much less than it is from warmer water. Mm-hmm. But a full answer requires me to get the equations to you, if that helps. Everything helps, because I have a similar lake. This is very cold water, but it's not in the Arctic, but in the Brenta Dolomites. So I'm very interested in such pattern for cold water lakes.
Oh yeah, but it's pretty interesting. So for instance, I've got a paper that just came out in, oh yeah, you can see it. This is in Nature, right? You can't read the title like that. Summertime increases in upper ocean stratification and mixed layer depth. And in the ocean, what they see is as the temperatures of the water are increasing, so is the mixed layer depth. And that follows from the fact that the water is warmer and the latent heat fluxes, that's evaporation, are larger, so you can deepen the mixed layer more. And I didn't point out very clearly
The same was even true in Tulik, although it was pretty subtle, so I didn't really show you. But that's also true there. And some of the papers that we're doing as we've lumped data with Gleon doesn't show that pattern. Some of them are showing a shallower upper mixed layer under heating, but that probably also means there's more phytoplankton or there's more dissolved organic carbon coming in, increasing the absorption of heat, right? But also increasing the stratification. So you have to take into account what's going on with the attenuation coefficient, right? The properties of the water, because that's also influencing whether or not you're going to have a deeper or shallower mixed layer, and wind speeds, okay?
Okay. And then I just wanted to add that we also saw in Lake Dowell that with high lake Wedderburn number, also greater than 10, we also had mixing events. And we could show this by calculating the difference in conductivity between the upper and lower layer. So the conductivity increased. So we could show this indirectly because temperature did not move. There was no mixing owing to temperature, but the conductivity there was. So it's a similar case as we told before.
But okay, remember, so one, it could be mixing, but two, because of the amount of time that I've had here for giving lectures, I haven't talked about processes occurring like in nearshore regions versus offshore, right? So you have the case if you warm the water more near shore, you get overflows. If you cool the water more like at night near shore, you get underflows. And then when you have streams coming in, they can cause mixing. But the one thing, again, if you have found, if in your lakes you find those Wedderburn numbers go, maybe the mixing occurs at 15, that information helps us improve the kind of paradigms we have for scaling, because the interpretation of Wedderburn number is based on the data that we've been collecting. It's not, there's a term, a Richardson number, which I didn't define for you all, and its cutoff is 0.25. It's going to be turbulent, above it won't. But a Wedderburn number is one that we begin to understand as we do experiments. And I did finally, working in one of those small lakes I mentioned, Lawrence Lake, I finally got software to interpret the acoustic Doppler velocimeter data that we had taken near shore. And it was pretty cool, because even then dropping to a Wedderburn number of 12, in the very near shore, I could see that there was some mixing going on. Right? So I won't disagree with you, but a question would be how spatially variable is. Is it just in a few locations, or is it across the whole lake? Does that help?
Yeah. It helps a lot, of course. So I thank you a lot for your detailed answers. Thank you very much.
Sure.
Okay. Thanks very much, Sally, and everyone for their questions. I just posted a message into the chat there, and Sally, we're seeing a lot of people that are interested in continuing this tomorrow at the same time.
Well, I'm actually seeing that there's a number of people who are.
Yeah. Oh, yeah. That's. Yeah.
I'm seeing it, and so I'm really happy to do that. And since I showed some things already, by going over, I think it also opens us up for conversations like we've just been having, which I think, that's when it gets interesting. And if any of you want to bring some data you've got and we could discuss what does it mean, I'd be more than happy to do that as well, not just have me talking. Okay?
Yeah. Okay, that would be great. We'll set up a Zoom link again, and we will circulate that today, so people have it for tomorrow. And just to remind people as well that these are being recorded, so if you're unable to make it as well, they will be posted on the Gleon YouTube channel and shared with everyone who attended afterwards. But
Okay.
yeah. Oh, sorry.
That's great. And then you'll send out an email to people to know that it's happening for those who already had to leave early.
Yeah.